Hi, my name is Sophie McCabe. I am a second-year chemical engineering student enrolled in Physics 2212, and today I will be presenting my findings on Lab 1. In my presentation, I will have three sections. The first is an introduction, where I will discuss the purpose of the lab, the fundamental principles involved, and a summary of my results. Second, I will be discussing my data, measurements, and observations in both the physical experiments and in my GlowScript model. Finally, I will be concluding my presentation with my answers to a few thought-provoking questions. The purpose of this lab is to use tapes to model the transfer of charge to create charged objects and observe how they interact. This is important because this lab illustrates the basic concepts that govern the motion and the interaction of all electrically charged particles and objects that we see in our everyday lives. The fundamental principles showcased in this lab is Newton's first law and Coulomb's law. Newton's first law states that an object in motion stays in motion and an object at rest stays at rest unless a net force acts upon it. Coulomb's law states that the electric force of magnitude and direction are governed by the relative size and sign, either positive or negative, of the two charges involved, respectively, and that the magnitude is proportional to the inverse square of the distance between the charges. This means that, like the gravitational force, when the two charged objects are close by, the electric force plays a huge role in their interactions. However, when the two objects are far away, the electric force plays a very small role in the interactions. Throughout this experiment, I have found that the interactions dictated by the electric force hold true and that these interactions are strong enough to rival the gravitational force. For the first exercise, I created two charged U-tapes of approximately 0.173 meters in length. When I charged the pen to be negative, I found that the charged U-tape was attracted to it, indicating that the tape is positively charged. For the main experiment, I was tasked with estimating the amount of excess charge on the U-tape. I was able to accomplish this knowing that the U-tapes were positive charges and thus would repel, based on my knowledge of the electric force and my results for the first part of the experiment. To set up this experiment, I stuck one of my U-tapes loosely to two chairs and then brought another U-tape of 0.173 meters in length and 1 × 10⁻⁴ kilograms in mass to the loose tape so that the repulsive electric force pushed the tape upwards until it came to rest, indicating that the electric force pointing upwards in the positive y direction completely canceled with the force of gravity acting on the tape pointing in the negative y direction. In other words, because the momentum of the top tape is not changing, the net force must be 0 in the y direction, and thus the magnitudes of the electric force coming from the bottom tape and impacting the top tape and the gravitational force coming from the earth must be equal. In the calculation of the electric force from the bottom tape to the top of the floating tape, I measured the distance between the centers of the two pieces of tape and used this to execute the calculation. Throughout my 3 trials in my experiment, I found that the average distance was 0.027 meters. Based on this information, I was able to conclude that the magnitude of the gravitational force on the floating tape was 1.7 × 10⁻³ newtons, and the magnitude of the electric force on the floating tape from the bottom tape was 1.7 × 10⁻³ newtons as well. In order to code this model on GlowScript, I calculated the electrical and gravitational forces for the tape. Following that, I illustrated the forces on the top tape as vectors on the point charge-less objects. I then calculated the total charge on the tape, knowing that both the tapes had an equal charge, so I could say that charge 1 times charge 2 in the numerator of the electric field calculation was equal to the 1 charge squared, so I rearranged the electric force calculation formula to solve for that. This charge value for the piece of tape was calculated to be 1.17247 × 10⁻⁸ coulombs. I calculated the total number of electrons by dividing that charge by the charge of 1 electron. In order to make these calculations, I assumed that there was no air resistance. I treated each tape as a point charge with the charge concentrated at its center, and I assumed that each U-tape I made had the same charge along the entire surface of each tape. Before I conclude, I would like to address 2 final questions. First, had the charges between the protons and the electrons been flipped, nothing would change in the interactions between the U-tape and the other objects would not have been reversed. This is because like charges would still repel and opposite charges would still attract. This is proven in the math since the electric force equation relies on the product of two charges, so the result of like versus opposite signs would not change because ultimately the shift in the sign and the force, the direction, would not be affected by this complete shift in perspective. Finally, it is important to handle the tapes as little as possible because people are conductors. This means that handling the tapes would give an excess charges a path to move to neutralize the tape and the person connected to the system. In this specific instance, had I touched the tape, some of the electrons in my hand would transfer into the tape to balance that net positive charge. This would make the tape either significantly less charged or completely neutral. Thank you for your attention, and I look forward to continuing this investigation into electricity and magnetism in Lab 2.